Hello everyone, my name is Charitha Saumya. I am a PhD student at Purdue University. Today I am going to present our paper DARM Control Flow Melding for SIMT Thread Divergence Reduction. Modern GPUs contain more processing cores and higher memory bandwidth compared to CPUs. GPUs can execute thousands of threads in parallel. Highly data parallel applications in areas such as machine learning and scientific simulations are ideal for GPU computing model. However, it is tricky to get performance for irregular applications on GPUs. Irregularity mainly comes in two forms. Irregular memory access patterns can stall the progress of multiple threads. This is known as memory divergence. Also, threads can take different paths through the program when irregular control flow is present. This results in control flow divergence. In this paper, we focus on control flow divergence problem in GPUs. Let's see why irregular control flow is bad for GPU performance. To understand why irregular control flow is bad, let's look at how GPU threads are scheduled for execution. GPU threads are arranged in groups called warps or wavefronts. Warp is the smallest schedulable unit in a GPU. All the threads in a warp must execute instructions in lockstep. This architecture allows GPUs to achieve massive parallelism and good energy efficiency while supporting a SPMD-style programming model. Consider this simple GPU program. In this example, we have a warp with 4 threads loading 2 values from memory, performing a multiplication and storing the result back to memory. All threads in the warp execute the instructions in lockstep, achieving good parallelism. Now, what happens if the program reaches a branch? In this case, branching condition is clearly divergent. In other words, the branching condition depends on data. Therefore, threads may want to take different control flow paths. At divergent branches, the execution of GPU threads should be serialized to maintain the lockstep execution. In some cases, loss of parallelism caused by this serialization can be a significant performance bottleneck. An interesting observation is that most of the divergent code paths contain many common computations. In this example, basic block B and C contain a common instruction sequence consisting of load, multiply, and division instructions. However, they are executed twice due to the serialization. Ideally, these common instructions can be executed in a convergent manner, avoiding the redundancy as shown in the diagram on the right. Here, the common instructions are merged and executed together. The rest of the instructions in the divergent blocks B and C follow the usual serialized execution. Existing compiler-based solutions are rooted in this simple idea. For example, tail merging can be applied when a set of basic blocks have identical instruction sequences at their tails and all the basic blocks have a common successor. In this case, the identical instruction sequence can be moved to the common successor. Select operations are inserted to make sure that the merged instruction consume correct operands. This reduces divergence because less instructions are serialized during lockstep execution in the tail merged control flow. Branch fusion is a more general version of tail merging. Branch fusion works even when the common instruction segments are scattered over the divergent basic blocks. In this example, basic blocks T and F have many common instructions, but all of them are not at their tails. Branch fusion works by first computing an alignment of common instructions in 2 divergent basic blocks. Dynamic programming based sequence alignment algorithms like Smith-Waterman can be used for computing this alignment. And then aligned segments of instructions are moved into convergent blocks. In this example, aligned instructions are shown in green and their new locations are shown in blue. This reduces divergence because more instructions are executed in a convergent manner now. However, one limitation of this technique is that it does not work across basic block boundaries. In other words, it can only merge diamond-shaped control flow. Now let's look at a real-world example with more complex divergent control flow. This is a CUDA implementation of bitonic sort. Its control flow graph is shown on the right. Bitonic sort is a well-known parallel sorting algorithm. This kernel contains a divergent if-then-else branch inside a doubly nested loop. And the if and else paths of the divergent branch contain control flow regions with similar computations. Tail merging or branch fusion can't be applied in this case to remove divergence because these techniques cannot merge at control flow region level. Also, the divergent branch is contained inside a doubly nested loop. This amplifies the effect of control flow divergence even further. To solve this problem, we propose a new compiler transformation called control flow melding that can merge control flow at region level to reduce divergence. The melded control flow is simplified and has less divergence. We propose divergence-aware region melder, DARM, that can find and meld similar control flow regions to reduce control flow divergence. We provide an implementation of DARM in LLVM, and we evaluate DARM on a set of synthetic and real-world benchmarks to show its effectiveness. First step of DARM is identifying divergent regions. A divergent region is a control flow region that has two properties. First, the region entry must have a divergent branch. To decide if a branch is divergent or not, one can use divergence analysis. The second property of a divergent region is the two successors of the entry block must not post-dominate each other. Next, we split the divergent region into single entry single exit subgraphs, also known as SESC subgraphs. A SESC subgraph can fall into two categories. First category is a single entry single exit region with more than one basic block. In the example CFG shown here, subgraphs B and C are two SESC regions. Second category is a basic block with a single successor and a predecessor. Subgraphs A and D are examples for this case. Next, we define when two SESC subgraphs are meldable. Here, meldable means the ability to merge two SESC subgraphs into a new SESC subgraph that is less divergent. For this, we consider three cases. The first case is region-to-region melding. Here, both the subgraphs have more than one basic block and they are isomorphic. So the melded subgraph will have the same control flow structure. In the example given here, subgraphs L and M have the same control flow structure. We can meld the corresponding basic blocks in L and M to obtain a new subgraph N. Second case is basic block to region melding. In this case, we expand a single basic block to match the structure of a region so that they become isomorphic. Consider the subgraph L and M in this example. Subgraph L contains a single basic block. Assume that we want to meld basic block A with basic block E because they have many common instructions. First, we create a new subgraph L' that has the same control flow structure as M. We place basic block A in L' in the corresponding position of E in M. In L', we need to make sure that the basic block A is always executed. We concretize the branch conditions in L' to achieve this. In this example, branching condition at the end of basic block R1 always evaluates to true. Values produced in A must reach their users. We insert additional phi nodes in L' to make sure that these values flow to all their original users. In this example, a phi node must be added to basic block R2 to flow the values produced in A. More details about how we insert these phi nodes can be found in our paper. Now, subgraphs L' and M have the same control flow structure and L' behaves the same way as original subgraph L. We can meld L' and M to obtain the subgraph N. We refer to this process as region replication. Region replication is useful when melding if-else-if chains with similar computations. Third and final case is melding a single basic block with another basic block. A divergent region can contain multiple SCSC subgraphs in its divergent paths. Therefore, we need a strategy to decide which pairs of subgraphs to meld. We align subgraphs based on their melding profitability using sequence alignment algorithms. Melding profitability is a metric computed at compile time to approximately measure the similarity of two SCSC subgraphs. It is computed based on the instruction frequencies in the two subgraphs. If two subgraphs have many common instructions, their melding profitability is high. For each aligned pair of subgraphs, we need to compute an instruction alignment to generate the melded code. To do this, first we linearize the corresponding basic block pairs of the subgraphs in pre-order. Pre-order linearization is used here because parent basic blocks are processed earlier than their children. This makes the code generation process simpler. Then for each corresponding pair of basic blocks, we compute an instruction sequence alignment. Instructions with the same opcodes must be aligned together. We prioritize isomorphic long latency instructions to be aligned together because avoiding the serialization of long latency instructions can improve the performance more. In order to achieve this prioritization, we use an instruction latency cost model. This formulation of instruction alignment problem is solved using Smith-Waterman algorithm. In the code generation step, we use the computed instruction alignment to generate the melded code. We start by generating the melded control flow subgraph. And then we populate the basic blocks of the melded control flow using the computed instruction alignment. For each aligned instruction pair, we generate an instruction with the same opcode. The operands of the melded instruction are conditionally selected by inserting select operations. Note that select operations are not required if the corresponding operands of two aligned instructions are the same. This instruction generation process is similar to the one used in branch fusion. Several additional steps are required to ensure the correctness of our transformation. For instance, melding can break use-def chains that go through the melded subgraphs. In this example, assume we want to meld subgraphs S sub t and S sub f. Here, instruction A dominates the use at instruction X. If we naively meld the two subgraphs, A will no longer dominate X. This breaks the static single assignment form. To solve this problem, we introduce a new basic block with a phi node. Phi node makes sure that existing dominance relations are preserved after the melding transformation. Here, the introduced phi node M takes the value of A and all uses of A are replaced with M. Next, let's look at how phi nodes are melded. Phi nodes cannot be melded just like any other instruction. They always appear at the beginning of a basic block. Therefore, we can't add select operations before them to conditionally pick their operands. Instead of merging, we copy phi nodes into the melded control flow regardless of their alignment status. In this example, align phi nodes P1 and P2 in corresponding basic blocks C and R are both copied into the melded basic block C_R. Another important aspect of the melding transformation is to handle instructions that are not aligned with any other instruction. In this example, instructions A and B are unaligned. One option is to fully predicate unaligned instructions, executing them in all divergent paths. However, divergence analysis can have false positives. Therefore, fully predicating unaligned instructions can incur extra overhead. Also, instructions with side effects such as stores are not safe to fully predicate. To avoid these shortcomings, we generate code to conditionally execute unaligned instructions. We call this process unpredication. Unpredication moves the unaligned instruction into new basic blocks and add phi nodes to ensure their values are flowed to users correctly. More details about these steps that ensure the correctness of control flow melding are provided in our paper. We implemented DARM as an LLVM IR transformation pass and integrated it with LLVM optimizer. We use LLVM's built-in divergence analysis to detect divergent branches during the analysis phase. Currently, we target AMD GPUs that support the ROCm toolchain. Our pass only transforms the device code. Therefore, we modified the device compilation pipeline in ROCm HipCC compiler to include our pass. We evaluate our approach on AMD Radeon Pro Vega 20 GPU against fully optimized baseline and branch fusion. DARM subsumes branch fusion. Therefore, we implemented branch fusion on top of DARM for the comparison. We evaluate the performance of our technique in two ways. First, we assess the generality of DARM using a set of synthetic benchmarks with various divergent control flow patterns. Second, we evaluate DARM on real-world benchmarks with divergent control flow. Most benchmarks are obtained from well-known benchmark suites and they are heavily hand-optimized. Let's first look at the evaluation on synthetic benchmarks. The plot shows the speedups obtained for each program varying the block size. DARM can successfully reduce divergence in variety of cases, achieving 36% geomean speedup over the baseline, and it is more general than branch fusion. This plot shows the speedups obtained for real-world benchmarks for various possible block sizes. Bars with plus sign denotes the best performing block size for the particular benchmark. Bitonic sort, PCM and NQueen's benchmarks contain divergent chord paths with control flow regions. Only DARM can successfully meld them to reduce divergence. We also observed that melding shared memory instructions is crucial for achieving good performance. Bitonic sort and PCM benchmarks use shared memory inside their divergent regions. In most cases, DARM either improves or matches the performance of branch fusion or baseline, and it achieves a 15% geomean speedup over the baseline. This shows that DARM can improve the performance of real-world benchmarks that are already heavily hand-optimized. This table shows the compile time overhead added by DARM. Compile time overhead is not significant for the benchmarks we evaluated on. DARM uses expensive instruction alignment algorithms to align instructions which can increase the compile time. However, DARM's instruction alignment happens at the basic block level. Most real-world programs do not contain basic blocks with a large number of instructions. Therefore, this overhead is manageable in most cases. We also profile the benchmarks using ROCprof GPU Profiler to collect various hardware statistics including ALU utilization and memory instruction counters. More details about these studies can be found in our paper. To conclude, we observe that existing compiler-based divergence reduction techniques are not capable of merging control flow at region level. We propose a more general transformation called DARM to fill this gap. DARM is effective at reducing divergence in real-world GPU programs. For future work, we plan to apply DARM in several other applications, including code size reduction and accelerating program testing. Our code and benchmarks are publicly available on GitHub. Also, you can contact the author at the provided email address. Thank you.